Hello, everybody. I'm at home, sadly with COVID, but I want to give you an opportunity to an exploration lab while I'm gone. And so I'm trying to think of the best way to do that. And so I think I've created something that is doable by you and interesting to explore. This is a laboratory that is really asking the question about what affects the speed of an object at the end of a ramp, but it's a little bit more in depth than that. Think about roller coasters, for instance. There are lots of different ways that they can accelerate their cars, and I want to look at kind of how the speed is determined based on some different scenarios. So first, we're going to be looking at a scenario just like the one down here on the bottom, where I've got a ramp where I'm going to be placing a ball bearing at different positions up the ramp with the same ramp angle. And the ramp itself that I'm using looks like this. So I've got my ball bearing in hand, and then I've got a ramp that I've put here. So if I place the ball bearing on the ramp and I allow it to roll down, that's what I've got. We're going to keep the same ramp angle, but I'm placing it at some different positions higher and higher up the ramp. Now, I expect that the velocity is going to increase at the bottom here as I bring it up the ramp, longer on the ramp, giving us a longer amount of time to roll. However, the question that I'm really looking for here is how does the pattern change? Meaning, is it linear? If you bring this ball further and further up the ramp, does that mean that the velocity continues to change in the same way? Or is it not linear? Maybe it increases faster, meaning I bring the ball twice as high, but the velocity is four times as great. So these are the types of things that I'm looking for here. Next, we're going to go ahead and take this ramp as well and allow the ball to roll down, but at different starting angles. And so the ramp will be at 2.2 and 4.4 and 6.6 degrees, but allowing the ball to roll down the same distance down the ramp, which is 80 centimeters or zero point 0.8 meters down the way. And we're looking at how the velocity at the bottom changes. And finally, this last one might be the most complicated to set up, but it is the last one that I'd like to give you a chance to do on your own in the classroom itself. And so I have three different ramp angles that are put at 2.2, 4.4, and 6.6 degrees, but attempting to have the exact same starting height for the ball bearing for all three of them. And so with that same starting height, looking to see what the final velocity will be down here, even though the ramp angle is increased, but the starting height has stayed the same off of the table. So let's see how we do the first ones. I did some help originally so that it will move things along a little bit faster. I created some videos at the top for each of these of the ball rolling down that 2.2 degree angle here. And then this one is at 20 centimeters from the bottom of the ramp. So that's here at 40 centimeters, 60 and 80 centimeters from the bottom of the ramp. So first we're looking at the starting height from the table. Of course, the starting height from the table keeps increasing. So in order to figure out this height, we need to use some of our helpful trig functions to be able to get there. And here it is. So that the height itself is equal to the sine of the angle, which is the 2.2 degrees, times the distance up the ramp, which is your hypotenuse, and then that gives us our y value, or our height here. I suggest that we use a little program called Desmos Scientific to be able to get there. And if you go to Google and you type in Desmos Scientific, then we can click here and it'll bring up Desmos Scientific when we're ready to roll. I need to go ahead and type in the sine of my angle, which was 2.2 degrees, and I'm going to multiply that times the height up the ramp. So the first one is 0.2, which means that my height off of the table is this value here, or 0.0076 or 0.008, and that's in meters. So I'm going to go ahead and type that one in here, 0.008 meters. That's how high it is off the table for that starting height here. Next, we've got our change in position. Now, careful, the change in position is not going to be the 0.2 meters, because I'm going to use these three quantities down below here to be able to determine the speed, or these two quantities to determine the speed. So I'm going to use this video here of the ball rolling down the ramp. So if I click here, it brings up this video that I took just at the end of the ramp itself. And if I hit play, we're going to see that the ball's rolling down the ramp there. I'm going to use my period and my comma keys to step forward here, and I'm going to use the front of this ball bearing as the part that I'm looking at. So I'm going to back that up till the front of the ball bearing is at the 1 centimeter mark. So right now it's about the 1 centimeter mark. And I'm going to check how many frames it takes before this ball bearing gets to the end of my bit. So I'm checking the velocity right at the end by going, how many frames does it take to travel that 1 centimeter? So 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, no, 10 seems too much. 9 seems about right. So 9 frames to travel the 1 centimeter at the bottom of the ramp. So my change in position, I'm going to go in and put that in here. My change in position is 0.01. This is in meters. That's that last centimeter that I've got. And the total change in time is 9 frames, but I filmed this at 240 frames per second. So that can be determined here by 9 divided by 240, which gives me this value of 0.0375. That's my amount of time. So this 9 over 240, that's 9 frames happening at 240 frames per second, which gives me a value of 0.0375 seconds. Last, if I'm going to calculate my speed, I need to take my change in position down my ramp divided by my change in time down the ramp, and I'll do that here. So my change in position was 0.01 meters, divided by the 0.0375. And that gives me a value here of 0.2666666, or 0.267. And I'll go ahead and put that back over here. So my velocity is 0.267, and that's in meters per second. So now I have a value for the speed at the bottom of the ramp when I allow the marble to roll, or this ball bearing to roll, 20 centimeters down the ramp at a 2.2 degree angle. I'm going to have you do the same thing with the same 2.2 angle, but we now have a new starting height, so you need to calculate that one here. And we'll have a new change in position. You could do the same 1 centimeter if you want to, or you could do a couple centimeters. Then you'll need to find out how many frames it took for it to go that centimeter or a couple centimeters, and then divide to be able to get your speed. You're going to be using these different videos to be able to find those out. We're doing the same thing down here, only now we've got different starting ramp angles, but the distance down the ramp is always this 80 centimeters, and you'll use these 3 videos to determine those. And then last but not least, I'll have some equipment in the classroom for you to try out doing your own. Notice I don't have any videos on these ones here to see if you can find the same for these. You will need to record the video. You can work in groups to be able to do that, to be able to determine how fast the ball is rolling at the bottom of the ramp. So that's the final challenge for you. In the end, there's a post-lab analysis here to be able to look at the patterns that you see and some predictions based on what you found. And then last but not least, a question of what if the ramp was not a straight ramp? What if it was a curved ramp instead? How would that affect the speed of the ball at the end? And these are predictions, so you can't get them wrong. You're just making predictions based on what you've got. So that's the work as a whole. I wish you the best of luck on this. And if you've got questions, you can send me emails and or text message, and I'll try and do my best to answer those as I go. All right, good luck, and I'll see you when I get back on Monday. Bye-bye.